Chapter 2, Atoms and Elements. Oops, no problem with the screen, of course. Okay, so let's think about what would happen if you took a piece of graphite from the tip of your pencil and broke a piece off, and took that little piece and cut it in half, and then you took one of the halves and cut that in half, and you took one of those halves and cut it in half. How far could you go? Could you divide it forever? No. Eventually, you're going to get to the smallest piece of matter in graphite, which is a carbon atom. So this was a question that people back BC were thinking about. And that's where our word atom comes from. It's from the Greek word atomos, meaning indivisible. So the idea is that you cut a piece of graphite in half, eventually you're going to get down to the smallest pieces. I said last week, I think of atoms as being a lot like individual Lego bricks. You could take a big Lego structure. Have you ever seen one of those like Death Star sets? They're like $400, right? Huge. Well, you could break that in half, and you could break part of it, and you could keep breaking it, right? Until you got down to individual Lego pieces. Can you break individual Lego pieces with your hands? No, you can't. So you get down to the smallest piece. Those are indivisible. So atoms compose all ordinary matter. If we want to understand what matter does and how to make it do what we want it to do, then we have to understand what the atoms are doing. So, 1827. Again, I'm going to throw some names and some dates in here. I am not testing you on those. Those are just, for context. A guy named Robert Brown was looking through a microscope at water-suspended particles that had come from pollen grains. Okay, and he observed something very interesting. So let's watch this YouTube video and see the sort of thing that he saw. So those are the particles that he saw. You see how they're wiggling? Some YouTube videos are a little more exciting than others, aren't they? That's maybe not the most exciting video. But we saw that jiggly motion, and he was curious. Why were those particles moving? Was the table shaking? They kind of look like they're alive, don't they? They look like they're maybe little amoebas or something, and they're wiggling and jiggling around. Well, at first he thought they were alive, but he finally figured out that the source of the motion was not coming from the particles themselves. So what was making them move? So Robert Brown observed Brownian motion, which is named after him. It wasn't until later, about 1905, Albert Einstein actually developed a theory that explained what this motion was. And Albert Einstein explained it as being a result of the molecular bombardments of the particles due to the thermal energy of the surrounding water. So in liquid water, you have water molecules. Those molecules are moving. They are vibrating, and they're also sliding past each other. The water molecules bump into these particles and cause them to move. The water molecules are too small for us to see in a microscope, even a very powerful microscope. But those larger particles from the pollen grains are visible under a good microscope. So the water molecules are bouncing against those pollen and dust particles. It's a bit like a beach ball that's thrown into a crowd, say at a graduation ceremony. You big crowd, you throw a beach ball, and somebody hits the ball, and it goes up, and then somebody else hits the ball, and it just bounces around very randomly. We can think of that happening to those particles in the video. They're being hit by the water molecules. So this didn't prove the existence of atoms, but it inferred the existence of atoms, because atoms explain how that motion could come about. So Einstein, his work and the work of others, removed any doubt that scientists had about the particulate nature of matter, that there were individual smallest particles of matter. Before that, it was, they thought there were atoms, but they couldn't really prove that atoms existed. So any questions about that? Fast forward to the 1980s. A couple of scientists at IBM in Switzerland, their research led to the development of STM, scanning tunneling microscopy. And this is a really cool technique that gives us the closest thing to a picture of atoms that we have. So the way this works is there's a tip on this microscope. It's held on this, I don't know what you call that, a probe. And this probe is controlled by a computer. And so they can move the probe back and forth, that's called rastering, move it back and forth across the surface. They control the vertical movement of the tip by monitoring the current between the tip of the probe and the surface that they're examining. By maintaining constant current here, they maintain constant distance, because electricity is jumping through that space between the tip and the surface. And in order to keep the current constant, you have to keep the distance constant. So they move this back and forth, keeping the distance from the surface constant. And so it's going to go up and down a little bit as there are imperfections or bumps in the surface of the material. It's called a tunneling current. Using STM, we can image and even move individual atoms and molecules. This picture here is the Japanese kanji characters for atom written with iron atoms, those are the reddish purple atoms, on a copper surface. So that's kind of fun to take atoms and spell atom with them. So let's watch a couple of interesting videos about this.
So what we do to move atoms is a variation of what we do to see the atoms in the first place. So we can't use light to see them. So we're not looking through a microscope like the conventional microscope we're used to. We need something that can see much smaller things than that. So what we do is take a sharp metal needle and bring it close to the atoms. And in a sense, we're feeling the shape of the atoms. So if you imagine that we have a surface that we're putting an atom on, we put it on the surface and so it holds still. What we do is take this metal needle close to the atom and sense its presence by measuring an electric current that flows. And as the tip of this needle approaches the atom, it sees more electric current, and we draw it up and over the atom to keep that current constant. So in a sense, we're feeling the shape of this atom. Then in order to move atoms, we observe that we have a sharp metal needle near it. We can bump into it by accident. What we can do is, instead of doing it by accident, do it under control. This is our atom on a surface. We can move the tip close, and we start to form a chemical bond between the tip and the atom. That chemical bond forms between most atoms. They like to bond to each other in most cases. So we start to form a bond such that the atom follows the tip around on the surface. We can drag it to a new spot. When we withdraw the tip, it holds still because the surface is holding it in place. And we can take an image and see where we've placed this atom. So that process, repeated over and over, is how we've built most of the structures in our lab. That's our bread and butter basic technique for moving atoms around.
Any questions? Do you understand what he was saying? I like the model he has there. He had a magnet in there. That's how he was making that ball move. that's the same sort of idea as to how they get the atoms to move. So they take that probe, and instead of just looking at where the atoms are, they actually get close enough that it starts to form a bond with an atom. And then you move the probe, and you can drag the atom over. And so you can move atoms around and put them where you want. Now, you can imagine that's a rather tedious process. Scientists do like to have fun. They sort of have their own geeky sort of fun, and so this is the sort of thing that scientists do when you leave them alone in the lab. So, that movie's not going to win any awards for its plot or acting ability or anything. But I think it can claim to be the world's smallest movie, right? Animated with individual atoms. I'll put these videos in our playlist on YouTube, and there's another one that is too long to show in lecture, but it shows how they made it, and that one's kind of interesting if you want to watch that. Any questions? So these sorts of pictures are the best visual representation we can get of atoms because they are so small. Here's some thoughts to help us grasp how small an atom is. So the Library of Congress, right, I believe it's in Washington, D.C., contains copies of virtually all the books there are, right? They have 35 million books in this library. And if you put them on a single shelf, the shelf would be 840 miles long, okay? So there's a lot of words in those books, right? If you took all of those words and wrote them in letters the size of those kanji characters out of individual atoms, all of those words would fit in an area of 5 square millimeters. Think about that. Atoms are very, very tiny. In spite of their mind-bogglingly small size, atoms are the key to connecting between the macroscopic world that we can see and the microscopic and submicroscopic world that we cannot see. Microscopic world is when you can see through a microscope. And actually, I've heard it called the particulate world, where it's the individual particles that's even smaller than microscopic. So an atom is the smallest identifiable unit of an element. There are particles that are smaller than atoms, but they are not individual elements, and we'll talk about what those are. So atoms, smallest unit of an element. So there are 91 different naturally occurring elements and over 20 synthetic elements. Periodic table was just updated about a year or two ago to add a few more man-made elements. Those elements are not found in nature, they're unstable, and so We can create them in a lab, but then they fall apart very quickly, so they're not going to be found in nature.